Welcome everyone. Today's session will be about two things. The first is the status of the Infinity and Beyond build. So Infinity and Beyond is the build which I am doing. Infinity is the name of the rover and Beyond is the drone. And in the second section, we'll go through human-robot interaction for rovers. So let's first go through my build status, what I have been doing on the past couple of weeks and what all things I have. The first is the status of mechanical. The chassis is almost done, and this is on the right side. What the figure shows all the parts that are actually needed, and on the left side it's my build. So I have almost all the parts except these outer wheels, which are kind of optional. Some people like print it, some people don't. I might in the next few weeks. And yeah, I don't have these pupils. It obviously makes it look a little bit prettier. I'll print it, and then I don't have this logo. But I think I have rest of the parts done. So the remaining task is to assemble these. So these require some screws called M3 screws, which I didn't know what they were. So I have to buy them, I think, and they are available on Amazon. So they should be arriving in the next 2 weeks. And then the status of the software and the simulator. So I tried this simulator, the simulation of the rover in the gazebo simulator using ROS. So this was a demo simulation provided by the ESA lab, which provides the design of this rover. I was able to teleoperate the rover in the simulator and move around the rover. The terrain is also provided in the simulator, which in the build. And these same teleoperated commands could be used on the actual robot itself. So the difference is basically the ROS nodes, instead of running in the simulator, they run on the Raspberry Pi. And then this was the simulator. Can you see the animation?
Yep.
Yep. So this, I was just moving around the camera view angle, and then I did more tests what is shown here. So I moved around it a bit, but this is only a section of the simulation tries I did. So it was working quite okay. And this was the control was basically through a browser. You could control the rover via the arrow keys on your keyboard, and the browser sends the commands to the ROS node in Gazebo. Then the status of electronics. I have got the servos. I think they arrived 2 weeks ago, and then I have the motor controller. They are basically servo motor controllers. They are 16 channel servo motor controllers, and these servo motors I think have a torque of around 155 Newton meter. I have not tested them yet with the because I don't have the power source yet, and I still need the wiring to arrive. So they will arrive with the screws and the step down voltage controller, and once they arrive in the next weeks, I will try to assemble all this electronics and mechanics together and try to bring up the Raspberry Pi along with this hat to control the rover. The status of RISC-V, I've done basic blinkies with FreeRTOS. Not much progress on that side. I think this RISC-V build will have slight delays. I was planning to buy a BeagleBoard based RISC-V, but they have cancelled that project. It was supposed to come out in April, and now it is not coming out at all. But I might buy an FPGA board later on and try to implement the RISC-V CPU myself. But this RISC-V will be delayed. So I am also running a parallel Raspberry Pi so that I can continue with all the building. And the video is the basic breathing LEDs with FreeRTOS. If I have enough time, I could replace the Raspberry Pi and buy a servo motor controller for this RISC-V board, and it has a Wi-Fi. So all the things that could be done on a Raspberry Pi could also be done via this. Arduino form factor RISC-V board. And then the status of beyond the drone. Last weekend I was able to play with it. So I used a Python SDK that is available to send some commands to the drone and operate it, asked it to take off, move around, and then land. How the drone operates is it has a camera facing downwards, and then it also has some infrared distance measuring sensors. And I think DJI uses this is a DJI Tello drone. It's called a Tello EDU drone that you could program with Python. The SDK is not provided by DJI, but somebody else has written the commands for it. And then they use something called visual processing system to use the downward facing camera and the infrared sensor to locate the drone from the position from where it took off. So it could locate where it is after it has taken off with that camera. But the problem with using that camera is like it only works under proper lighting conditions. So if it's not too bright, then the drone will find it difficult to stay in position and it will hover around. It is not very stable. And I think that same problem happens when it's too bright. There is one more camera on the drone, and it's a fixed camera. It's fixed to the body of the drone and it only faces one direction. That is a little limiting. I've seen some people use a mirror to change the field of view of the camera to downward facing and then use it for some line following and other projects. So I could try that. I could print a few mechanical structures to attach a mirror to the front facing camera and then maybe do some image recognition or landmark recognition with that. I tried around 4 commands for this trial. So the first command is like take off. It takes off around to 1 meters, then move up 100 centimeters, move forward 200 centimeters, and then finally land. So it was quite easy. There is one like simple commands, move forward, and then the parameters are in centimeters. You could give that centimeters. I think it's a text-based, ASCII-based interface. So the drone attaches to a specific IP, and then you could just send UDP packets to that IP in specific format, and the drone would respond. That is what the SDK is doing. So what are the next steps for me? For Infinity in mechanical division, I have to assemble all the parts, print the outer wheel when the screws and other parts arrive. And the same for electronics. I have to bring it up and test it with the Raspberry Pi, which I have, and the servo motor controller. For the software, my plan is the next step is to integrate the teleoperation with Docker. So I will be using Victor's code base as a starting point. I'll go through it and then maybe ask some help from Victor. And for beyond the same, the teleoperation is working, so I'll be integrating it with Docker and maybe also check how to enable remote access for all the things that are available on the API so that you don't have to be located in Finland to operate the drone. And as a stretch goal, I might add a camera on the drone. It's called ESP-I. It's a ESP32 based device. ESP32 is MCU with Wi-Fi. This is how it looks. So it's from a company called Espressive that makes Wi-Fi MCUs. And they have released this device called ESP-I. In addition to the camera, it also has a mic in it. I have 2 pieces of it. My plan is to attach one of this to the drone to have an extra camera and the other one with me. And then I could attach all of these to the same Wi-Fi access point and then give voice commands. For example, the things that I was doing from my Python SDK, I could just recognize my voice and then give commands, okay, take off, move forward, and then send specific commands to the drone.
Anuraj, what's the weight of this added ESP32 board, and how much payload capacity does the drone have spare? Like, have you done that calculation?
No, I have not done that calculation, but DJ has a new version of the drone. It's called RoboMaster TT drone. I'll just share. It has extra, let's say, ports to attach extra sensors to it, and then they are attaching it via ESP32.
Okay, so you're assuming that it has enough payload capacity to lift this extra
Yes.
circuitry. Okay.
Yeah.
Yeah, are you sharing some web page or something? I
Yeah.
think we can't see it.
Can you see
in
it
the-
now?
We're just seeing the next step slide.
Ah, okay.
Yeah, I think you were sharing the application
Window.
instead of your screen.
Yeah. Is it visible now?
Yeah.
So this is a new version of the drone. This extra appendage that you see, it's internally it's ESP32 way, and then it attaches to the USB. But they charge like $150 for this. And since they don't release the firmware, this is, if you want to do this, then you'll have to spend extra 150. But there are other ways to do it. My plan is to not modify the firmware on this drone, but just use an ESP32, which is basically this port. So I could use directly this port and attach it to the same Wi-Fi access points. And instead of spending, let's say, $150, I could do this in $50.
ESP32 is just Arduino with Wi-Fi, right?
Well, the processor is different. The processor is, I think, some Extensa L7 board. I think it's some MIPS based, but I'm not sure. So it's not Arduino based. The Arduino framework has been ported for it. There are libraries for it in the Arduino framework that you could just use with the Arduino IDE. So it works with Arduino, yeah.
So it would be independent of the rover, right? Like it will be in the same network and using some ROS nodes or something to communicate with each other. Like,
Well, my first year plan was replicate what is happening on Mars right now with Perseverance and Ingenuity. They are two separate parallel projects, and you could operate each of them.
okay.
So, and yeah, if I could integrate both of them together with the same user interface, that would be something nice to have. But my first year goal was to build some platforms for teleoperation and then build upon that in the next year.
Okay. I had a more specific question, like in the, what is it? In the drone, you are attaching a new component, right? That would be connected to the drone via the network only. It's not like you are connecting it in the firmware or in the circuitry of the drone itself.
Well, to connect it to the drone directly with the extra things they are providing, I would need access to the firmware and flashing it. Like some people have reverse engineered and dumped the firmware, but it's really time consuming and hacky way to do it. I not prefer spending my time on reverse engineering, and rather I would do more robotics.
Yeah.
Are you going to use the power off the drone?
So
Like a vampire?
Sorry, I didn't understand your question.
How are you going to power the camera?
Well, for that, I will have to do some hacks. I will be drawing it off the battery that is already there. Some people have attached Raspberry Pi on the drone. So the drone is able to carry the Raspberry Pi and power it. So I might try something like that. Or maybe attach a lightweight battery. I don't know. I haven't decided. But that is a stretch goal for me. So that is something I'll try it out. Maybe if I have.
Yeah, that's why I was curious about weights. If you're even thinking of attaching a separate battery, that's a lot of weight. Batteries are quite heavy. Even a small battery.
I think you can. Well, the battery if you look at the batteries that are available in mobile phones, in the old Nokia mobile phones, they are quite light.
Yeah.
And you can have small like 1 inch by 1 inch batteries. And the battery on the drone itself lasts for around 13 to 15 minutes. That's it. So one flight is around 13 to 15 minutes. So if I draw from the battery on the drone itself, maybe it reduces the flight time to around 10 minutes. Okay, so why am I doing all this? Obviously, to have fun. So that is my primary goal. I have mentioned this lots of times in the previous sessions too. But what else? So I want to build some platforms to conduct my own independent robotics research. I have not done robotics research for around 5 years now. Building these platforms allow me to experiment various things I could have done if I would be doing like robotics research full time. So this is something I want to build for my own independent robotics research. And then also in parallel develop some skills in building RISC-V systems, the hardware, how the tool chain works, how the hardware works, and how the instruction set looks, and other things. But I think the RISC-V is a slow track in addition to the normal robotics track. Then we come to human-robot interaction for rovers. The origins of human-robot interaction, I think the first mention of it, at least according to Wikipedia, is by Isaac Asimov in the early 40s when he wrote his novel I, Robot, and then he stated the 3 laws of robotics. And in the second law, he mentions that a robot must obey the orders given to it by human beings, except where such orders would conflict with the first law. So this assumes there is some sort of human-robot interaction, and the robot is able to understand the commands given to it by the human. On the definition of it, according to this website, which is a research portal for human-robot interaction, is human-robot interaction is a field of study dedicated to understanding and designing and evaluating robotic systems for use by or with humans. So this assumes there is some sort of communication happening, and this human-robot interaction basically could be classified into 2 basic forms. One is teleoperation or remote interaction. That is primarily what we have been doing with the Mars rovers, so with which NASA has and other space agencies have sent on Mars or on Moon. So for rovers, primarily it is teleoperation or remote interaction. And the second form of interacting with the robot is when the humans and robots are co-located. So this is also called cobotics or cobots. So they are working in collaboration with the robots and they share the same environment. The rovers which have already been sent to Mars and that are currently working on Mars or Moon are primarily teleoperated. So all rovers before Curiosity and Perseverance didn't have much autonomy. They were primarily teleoperated. There was some pre-planning done in Spirit and Opportunity, but that was basically done by the humans here on Earth, and then the commands were sent. So there was no autonomous operations at all. The first teleoperated rovers were on the Moon. They were the Lunokhod missions, the Russian Lunokhod missions. This is quite relatively easier compared to teleoperating on Mars because the round trip time is about 2.5 seconds. So basically no delay. So you could know what is happening to the rover almost in real time. And then for Mars, the communication delay is around 14 to 20 minutes. So that is quite significant. That is a big challenge for teleoperation. So you are not knowing for 15 to 20 minutes after you have issued the commands to the rover. And I think this is the reason why Curiosity and Perseverance were enabled with some autonomous navigation capabilities, and I think it's quite advanced on Perseverance, and the Perseverance can travel up to 120 meters per hour, and I think both of them cost around $2 to $3 billion. And yeah, and on the right side you can see the distance traveled by each of these rovers over their mission durations. So the longest, is it visible enough, the distances? Yeah, so the longest distance is by Opportunity. I think it traveled around 45 kilometers, and then Lunokhod travel around 39 kilometers. And then the Apollo lunar rovers were basically jeeps that you could drive around. So they were traveling around like 35 kilometers, between 25 and 35 kilometers. For with autonomous navigation, Curiosity has been able to travel, I think, in 9 years, 20 kilometers. So that's half the distance of what Opportunity traveled in 14 years. So all these distances, yeah, they might be quite lot for what they are built for. I think Curiosity was built for around 3 months of mission duration, and it has been running for 9 years. So they were not meant to be running for such high distances, but they are still
I actually
running.
don't think that's true. Like, I think NASA has a history of basically sandbagging the capabilities. So they underpromise and over-engineer, and that way, when they actually end up far exceeding the mission parameters, it looks like it's been like unexpectedly successful.
Okay.
So I think that's what they do. They sandbag it basically. It's a good way to get money from politicians, where they
Okay.
feel like they're getting more than they paid for.
Yeah. But in order to study human-robot interaction with rovers, we need to know what are the kind of things the rovers need to do on the surface of Moon and the Mars. So this was a PhD study done in the lab I was in around 10 years ago. This study was done between 2008 and 2011. In the third chapter, it goes through all the activities that a rover could do on the surface of Moon and Mars. It's a literature review of these 5 studies. I think 2 of them are from ESA and 3 of them are from NASA, and then it kind of summarizes all these different studies done by ESA and NASA. This is a good table given in the thesis, which kind of summarizes all the different kinds of activities you could do. These are classified into geological, communication, and maintenance and repair and inspection. So in geological activities, you could do sample collection and then storing, and then identify different locations and the geology in which the rover is working. You could explore or scout terrain around and place different kind of instruments in that terrain. For communication, you could have a local network for the different instruments that you are placing there, and for the humans too, and then also the communication links to the earth. For inspection, maintenance, and repair, the different activities could be like assembling the different instruments and the maintenance of it, the transport of different stuff around. And on Mars specifically, dust mitigation might be an important activity. Like if dust settles on the solar arrays, then the solar arrays are not working and solar panels are not working. So that is one of the activities that was identified in this literature review. And these are kind of mission activities, and in the like document itself, they go into like detailed breakdown of what each of these activities would involve. So it's kind of a good document to go through. But all this research has been done with basic assumption that like nothing can happen to the rovers itself, like no risk at all. So, but the game totally changes if the rovers are cheap and disposable. Like, okay, the rovers has been stuck around, we throw another rover in that same direction and avoiding that obstacles. This is not the consideration all this previous research has been started from, and so this changes the game a little bit. So if you are starting with the assumption that the rovers are cheap and disposable, so what kind of things can we do? That is one of the things I would like to explore after building these platforms. So one obvious answer is like we could use the latest commercial hardware and software. So for example, we could be using the latest virtual reality or augmented reality developments for controlling our rovers, and then maybe the latest developments in natural language processing and natural language interface to command the rovers to do various activities. I think this is one of the research that uses
Drone augmented human vision.
so they are using some combination of augmented and virtual reality
User
to control the
looks
drone.
through a virtual hole to observe the scene. Red moving circle is the point user looks at.
Yeah, and the other form of interface could be just as speaking to the rover. But these are not straightforward, because one of the basic challenges is like how to have a common understanding of the environment around. So this is a research which I found yesterday, and in the conclusion they basically say that like how to communicate clearly about the goals to the rover, and the rover should be able to basically say and do things with after knowing the capability it has. So that is not a solved problem, and this is a really difficult challenge because humans and robots they think in different ways, and what might be easier for us to express in words, the robots might not understand at all. Or so the research which I mentioned earlier here basically uses affordance based communication. The concept of affordances was, I think, initially proposed by a psychologist named Gibson in the early 70s or mid 70s. Affordances are basically what the environment offers, kind of interactions that the environment offers to the agent. So this is the starting point for many of the research of Rodney Brooks, in which he uses the subvention architecture to build different kinds of robots. So the idea is you don't have symbols, but the agent is having direct action relating to the objects in the environment. Symbol based systems have symbol grounding problems. So for example, if you have a, let's say, concept of handle in your brain, you are not using that concept of handle directly, but there are direct relations to actions in itself. We don't use symbols for object manipulation. So for the babies, those who are born in like 2021, for whatever things that appear like a hand sanitizer, they think that it's a hand sanitizer. So this kind of suggests that like the learning system in our brains is not like completely symbol based, and then we use some sort of direct object action relationships in our brain, or we learn how to do it. So the babies don't use the concept of let's say handle. They don't need to know that this is a handle to actually hold the handle. For example, this cup, so they might not know that this is called a cup. They don't know this is called a handle, but they'll still be able to handle and grab it. But there are problems with trying to build systems which are just let's say affordance based, and for really complex robot they don't scale well, and this is still a challenging problem. Some sort of symbol grounding for the actions which we want to perform with the robot.
In such affordance-based systems, how are the affordances represented? Like, do you have like?
Well, in the thesis which was done, which I mentioned earlier, so the affordances were basically designed by the humans. I think that is one of the problems. Like, so the affordance was programmed by the human, so it was not learned by the robot. So a set of affordances, what the robot could do basically was hard coded, and then you could use like a human interface or the language interface to ask for an action, and the robot would find what it could do from those affordances. But that
Yeah.
But that
So
thesis,
the problem is like composing the affordances to do action. Is it like you have a bunch of affordances which is already hard coded or something, and you have to compose them to achieve a task?
yes, that was the suggestion in the thesis. But that thesis was done before deep learning took off. So I think that thesis was done between 2008 and 2011, and it assumed that natural language processing would not progress much in the coming years. And like, so it didn't use any machine learning. So a lot of it was hard coded. What can we do with the current state of the art natural language processing and machine learning? There have already been some research, like this is research found yesterday called affordances that uses end-to-end deep learning for finding the different affordances a robot could have in its environment. And then there was no GPT back then. Voice interface was also kind of hard coded, so you could just recognize the words. Okay, pick rock. So it would identify the phrases pick and rock, and then try to match all the different efforts that the robot had. But that is also changing, and with GPT we could or GPT like systems we could use a much more natural way of interacting with the robot. So
I want to interject something here. Like, I first heard of affordance from a study that was done at Park in the 90s called The Myth of the Paperless Office. And there they were talking about why paper will not go away because of like digital displays and ebooks. So this was, remember, before the Kindle and stuff. And there they used the concept of affordance in a slightly different way. It's basically the interpretation of natural properties in the context of a goal. So a piece of paper, for example, you can say it has the affordance of markability, which means it can hold marks made by a pen on its surface. Now that's a consequence of the property of paper. Same thing, like you can use a book to hit somebody on the head with it, right? So that's the affordance there is weight or club ability or something like that. Or you can use it as a doorstop. So that's basically, again, the affordance there is mass. So in the sense I have heard it used, affordance is basically an interpretation of form or structure in terms of like a function in an improvised way. So some functions are designed. So a book is designed to be read. It's not designed to be used as a club to hit people with, but you can use it that way, right? And the distinction psychologists make is functional fixedness. So if you can only see the affordances that have been designed into the object explicitly, that's called being functionally fixed. Whereas if you just look at it as a physical object or software object, and you see what can be done with it, that's sort of a more general way of thinking of affordance. So the way you are talking about affordance from this thesis, it's not clear to me that it's the same sense. So for example, when you say pick up a rock, you used that example before. The way I would think of that in terms of affordances is the rock has the affordance of pickup ability. That means it has like a gripability or something like that. And the gripper would have its own affordance of contractability or something, like it can grip, right? So that's, am I thinking of affordances in the same way you are?
Yeah, kind of. So basically, like the rover actually had a gripper, and all these affordances were kind of programmed into it. So the robot didn't learn it. So all these affordances for the gripper were already identified by the human being or the programmer.
So I will interject as well, because I think it's the same concept of affordance, okay, in a different era. And there is a subtlety, from my perspective, is that exactly what Anuraj has just said now, is that the programmer provides affordance, okay, by coding them into symbols into some program, basically. And it means that in the traditional robots, the software has access to those symbols, and it doesn't have access directly to the environment. And so this is what potentially deep learning can bring in, can improve on, is that instead of hand coding symbols, okay, this is a door, this is a table, and so on, it's using perhaps a deep learning component to create a symbol that makes sense to the robots, okay? And this is what could be pretty interesting and relevant in this context. Sorry, I had another point. It will come back later.
No,
I think, just to connect the two thoughts, I think the way I'm understanding it is, if you're designing the robot itself, you have complete control over the design. So you can sort of define certain aspects of the design as affordance. But since the natural environment also has affordances, for example, you can pick up a stick and poke something with it, or you can pick up a stone and throw. So it would be interesting to combine both notions of affordance, the designed explicit type, and then the sort of natural properties type. And one way to do that might actually be through VR or AR, where you scan the environment and simply put an overlay and say rock, and then you put a bunch of tags saying it can be thrown, it can be picked up, and then you almost turn it in, you almost overlay inferred user interface on top of the natural environment. So that might actually be a very interesting way to think about the non-designed environment.
Yes.
Yes. I have.
Sorry, please.
I have one question on why like you are saying, like before affordances there was something else, right? Like that is basically what Venkatesh was saying. Like book was meant to be read and you can throw it as something affordance that is by nature of the mass of or something. I'm just thinking back on why the concept of affordance came up. Like that came up because of before that were programs like made to do only one thing. Like even in a symbolic sort of system, you can pick up only this specific apple or something, or this specific box or something, and then it became a more abstract form of thing, like wherein you say if something has a mass, I can just pick it up, even though I have just hard-coded the action of picking it up. So you make an abstraction. I'm just thinking of how to, are affordances like a bit more abstract form of like doing some action? Is that even before all this deep learning and other things, like why did that concept came up in that paper or something?
I think originally it came up as a way for designers, like UI designers, to describe things, not so much as a way to design things. So I think the design use came after the descriptive use of the concept of affordance. So if you think of it from a psychologist's point of view, it's just looking at the environment and saying, all right, what all can you do with it? What kind of agency is latent in it? So it's almost an analytical description of the environment. But when you turn it into an engineering concept, then it becomes, all right, what affordances can you design into it? And then it's kind of like a simple mass is not particularly optimized or specialized for anything. For example, hammering, right? A rock can be used to hit somebody, it can be used to hammer something. But if you want to make a hammer, you will design it with like a handle and then a heavy part and stuff. So then you sort of optimize for one affordance, and then that becomes its sort of explicit function. But I think there's also a relationship to, in AI, what people call the frame problem, where the way I think, like now we're thinking about it in this machine learning open-ended way. But previously, I think the way people approached programming was simply, if it's, the only things you can do are what is defined as doable, and anything that's not defined as doable does not even exist in the universe. And that relates to something like the, what the AI people call the frame problem. So what's in the frame? Things change if you change them. Things don't change if you don't change them. And I think that's what's happening here. We are actually indirectly solving the frame problem by looking at the environment more generally in terms of what all can it do, limited just by the constraints of physics, as opposed to what all can it do based on the list of things I say it can do, right? So that's the spectrum. On one end, it's like white list of all the things it can do because I've said so. And on the other end, it's the blacklist of all the things you cannot do because of physics level impossibility. And I think as systems get smarter, they get closer and closer to the physics limit as opposed to closer and closer to the human design limit. Anyway, sorry, I didn't mean to go on a rant there.
Yeah, like one of the things in that research is basically it was difficult to find all the different kinds of affordances for an object for a human. But maybe we could use machine learning to find the different kinds of affordances that are already available.
But, so I think it's possible, but there is something that an affordance is also, there is a co-evolution basically with what we can do, because the robot or us, we do have some capabilities that are limited in themselves. Okay, so affordance is understood, I think, from what we can do in the first place. Okay, and so the example, I think a famous example is a doorknob, okay, a door handle. Sorry, it's in the design of emergency exit doors. Okay, I think in the past they were not designed as they are now, because usually emergency exit doors are also fire stopping in a way. Okay, and so they can only be opened in one way. And the thing that the design, so the affordance for these doors have evolved now and is pretty stable in such a way that the direction where you can open it, the only way you can open it is by pushing it. There is no handle at all. Okay, so the affordance has been designed for the scenario we want to solve. Okay, and if you look at those doors where they have no handle because they are open only one way, on the other hand, on the other side, okay, there is some mechanism where you have all the affordance to actually grab and pull it, okay, because the only way to open it is to pull it from the direction. And so there is this co-evolution that's happening, and that we can exploit as well. Okay, and so from the perspective of an autonomous agent, there is the problem of how can we make a robot evolve in the first place, because we are talking about hardware. Okay, and so under the assumption that we can't change that hardware, or we have a little room of adaptation, okay, maybe we can make a hand that has some capabilities, okay, but maybe not as many capabilities as the human hand or whatever. And so from with that constraint, what can we do? Okay, is an interesting point. So it's a bit longer than I expected, and still there is another point I'd like to make. Do we have time if I speak
I
more
think
now?
we have 15
So
more minutes.
the other point is that the way we are framing it here is that we have the environment, we have our robots, and in the middle, it's inside the road. In the middle, we have this how do we represent the environment? Okay. And the thing that some people think that they can use, for example, something like Alexa, okay, for the NLP part, okay, to say Rover go there, Rover go here, okay, and that it will solve it by itself, okay. And so the thing to understand here that is completely insufficient, because if we take any of our robots and we install the Alexa capability, what we will have solved is just the NLP part, okay. It means that the Alexa capability will be able to understand, okay, Rover go there, okay. But then the Alexa capability takes that in, interprets it into symbols, and after has to translate that into actions, okay. And it's this part that is missing, is how do we translate that into actions, okay? Traditionally, how it's done is because we have symbols, okay, this is a box, this is a table, this is a chair, okay, and we link what Alexa has passed for us into actions on that framed world. So it's exactly what Venkat explained, it's the frame problem, okay. And so how can we make that more flexible, basically? And so it's pretty clear that deep learning provides more flexibility here, okay? Because we can use deep learning to have more fuzzy understanding of what a chair is, or what a table is, okay? But even that, we have to understand that it's not enough, because assuming we have deep learning here to say, okay, this is table, and I'm pretty flexible on what a table is, what do we do with that? How do we build the action? And for that, this is where I'd like to frame the work I'm doing and the presentation we've made on abduction reasoning. Okay, it's about the use of maybe Alexa and deep learning and something like abduction reasoning all together. Maybe then enough or closer to do what we're talking about. Okay, in terms of an autonomous agent. So a bit longer. Thank you.
No, I think this is a very interesting bunny trail, and we should make this connection, because I think you just made an important one. The abduction reasoning talk you gave a couple of weeks back, that was mainly on the analysis side. So Sherlock Holmes sees a set of clues and asks, what's the best theory that fits the clues? That's abductive reasoning, right? I think what you're saying right now is you can also do abductive reasoning on the synthesis side, which is you're a robot and you're sitting in an environment with rocks and other things, and you have a problem, which is you must climb up to a particular hill and you can't do something. So can you move some rocks around so that you can actually do that? So you're in a way doing abductive reasoning on the synthesis side. So I think there's something very important there. And I was just reminded as you were speaking of I don't know if you guys follow the account 2-Minute Papers. So this is a guy on Twitter who does machine learning paper summaries. And one of the recent ones he did was some really good research by some people who had an environment with agents running around moving blocks. And they were basically playing hide and seek. And if the hiding team had to hide behind obstacles and the seeking team had to see them before a certain time. And the great thing about that research was both sides were running on deep learning and both sides were just figuring out how to use the block in really weird ways. So for example, in one simulation, the hiding team side robot, it used the block to block the entrance to the part of the domain it was hiding in. So the seeker side could not enter that part at all. But in another simulation, the seeker side found a way to stack the block against the wall and then jump up and see the hiding side. So all sorts of weird, unexpected uses of like just plain blocks. So these are not like specially designed objects meant to play hide and seek. These are random just blocks sitting around in an environment. I'll find the video and post it in the Discord. But this to me, I think is abductive reasoning with general purpose objects in a synthesis problem where there is no designed function at all. It's just objects sitting around and your only constraint is physics. If physics allows you to do it and you can figure it out by brute force search, you can do it. So I think that's the sort of ideal case we should kind of be, I don't know, aspiring to holy grail wise. And of course, doing it in like an actual rover environment as opposed to a simulated environment with blocks is very hard. But that's, I think, I don't know, there's something there. If you can get our rovers doing something like that, that makes them much more powerful.
Definitely. The paper you mentioned is from OpenAI. Okay, it was last year. Okay, and maybe it's just fun to look at in the first place. It's pretty impressive. Okay, what is very interesting is that the presentation I gave 2 weeks ago. So it was more about introducing the concept of abductive reasoning because it's mostly misunderstood. Okay, and I thought I was talking about how I was going to use it for us. Okay, because I talked about a soup of sensor signals we have. Okay, and how we can make sense out of that soup. Okay. That's the link here we have with the concept of affordance. I never saw it under that light. It is very interesting. Okay? And what's interesting is that the OpenAI paper on the hide and seek, they have no planning at all. Okay, so they are not using per se abductive reasoning, but what is possible is that they're using mainly reinforcement learning. Okay, and what is quite interesting is that what they have done. It's possible that we have emergence of some abductive reasoning inside whatever is happening in their data processing, basically. That's pretty mysterious. I will look into that.
I think we should definitely make a note of this connection. It's going to be interesting to explore.
Yeah, this one of the reasons I like made this. This has been good. Like I've been thinking about this like in the back of my mind since I think Eric gave the presentations. Like, what are the different ways in which we could interact with the rover, and what could the rover do in the environment? So I thought, okay, I'll start this basically a small presentation and see how the discussion proceeds.
Can we see this as, okay, from a very crude software engineering sort of way, can we see this as a program synthesis problem? Like, we want to achieve something and we have some building blocks, which we might know or we might discover. Maybe you can make the discover itself as a capability we have. And then we are just trying to form a program. Lift this rock and put it there might be an abstract command or a function. So essentially the bot has to compose the API of the real world and then try to achieve that problem as it's like in that way it's a symbolic problem, like you are trying to synthesize a program there, but how you do it, that is up to the solution finding mechanism that we have.
So just a quick answer is that yes, the answer, I think the answer is yes. It can be seen as program synthesis. Okay, but the thing that then pretty quickly we changed the terminology to talk about planning. You know, in AI, planning is a pretty old topic with many achievements. Okay, but most of the planning that we can see used, okay, is basically static planning. Okay, that we plan once and we execute. And after there is sometimes there is some kind of error handling happening, okay, in some frameworks, not always. And so the thing is that program synthesis, yes, but I would say perhaps what is more interesting and definitely more challenging, it's a dynamic program synthesis. It's all at runtime while we are acting, okay.
That I'm trying to think of an example of that, and the closest like practical engineering version I can think of that is actually CSS. So CSS, I think, is the only truly widely used declarative programming language, right? You just declare what you want the page to look like, and then the browser effectively does this in a fairly real-world environment, and the rendering sometimes does what you think it's going to do, sometimes it doesn't do what you think it's going to do. I never really got a good instinct for how CSS works, but if you can think about like, can you do CSS for the real world? So like the Captain Picard image you had there, I remember like his way of giving commands was something like make it so, right?
Make it so.
Yeah, so you want the make it so version of giving commands, declarative commands. I also wanted to like make one more point before I forgot. You cited the Asimov 3 laws of robotics, and it struck me that, and you made the point of if you start with the premise of cheap rovers that are disposable, the game changes. And it struck me that the way it changes is that the third law is basically deleted, where the first law is protect the humans, second law is obey the commands, and third law is do self-preservation, right? So if the human tells you go kill yourself, don't do it. Whereas if you have lots of cheap rovers, then you basically override the third law or make the threshold of activation very, very low. It's like, all right, if you ask me twice, I'll kill myself. You have to ask me twice, something like that. That was an unrelated point.
Yeah, but I think like you still have to be careful about the different instruments or the various things that are like statically kept, human-built stuff that is kept on the surface of Mars. That should not be maybe destroyed or maybe harmed.
So we should make our own 3 laws of rover robotics and say that okay, the fourth law will be a cheap rover will sacrifice its life for an expensive rover whenever possible. All right. Any other thoughts before I stop the recording on my end? I know Anuraj is also recording.
Any questions about my build?
Hey, for the 3D printing, how did you go about it? Very shortly, like, did you have a 3D printer or gave it to someone?
Well, I didn't know, and well, basically the last time I did some mechanics was in during my master's thesis. After that, I haven't touched anything, so I'm not a mechanical engineer. But then when the project started, I looked around. I was thinking of using some cloud printing and buy the stuff. And then they gave me a quote of 1,000 euros. And then I looked at the prices of 3D printers. It was like $300 or 300 euros. So I thought, okay, there is only one obvious choice for this. It takes some time in the beginning to set it up, like the leveling and stuff. But after that, it's done. Anybody could do it.
And I think 3 of us are doing 3D printing in this group, right? So you, Rhett, and me. And I think we can claim that's a competency in this group.
It's a lot of fun, actually.
Yeah, it is. Because you feel more like you achieved something, even though even if you just downloaded it and all you did was make sure it didn't stick or
Yeah,
something.
yeah.
It feels like an achievement.
Yeah, but one of the goals for me to buy the 3D printer was to learn some basic CAD. So my bachelor's was in electronics, and then I did my master's in robotics with some programming. But even during my bachelor's, I wanted to do some mechanics, but my course structures were so rigid that I could never learn some mechanics or CAD. So this was a good opportunity for me to start on that track.
Are you done with the PCs? On the photo where you compare the two photos, sorry, I missed the point whether...
Let me bring it up again.
I noticed that you didn't add a banana for scale.
It was my question. It was my question. Thank you.
Yeah. Yeah.
Yeah, I think I don't have the banana and the pupil and the outer wheels, but I think I have the rest.
Did you add eyebrows?
No, they are also like there are different kinds of add-ons for the head. So you could have eyebrows, you could have a hat, you could have a mustache. But that is something I will do later.
Yeah. Some yak horns?
Yeah, I think Venkat designed something. I would print that, maybe add it later. Yeah, but those are all cosmetic.
What about the tires?
Yeah.
Did you mention about the tires? Sorry, I missed that point as well.
So there is some.
Sorry, I accidentally stopped the recording. But
yeah, I have the. Yeah. So the outer wheel is basically for some protection of the inner wheels. So it's not mandatory. Some like a lot of people just don't print this part. So it goes out on top, like outside of on the circumference of these wheels. I have not printed.
Did you print that from PLA?
No, I don't have the PLA yet.
No, the outer wheels. Like, what material did you print them from?
Everything.
PLA.
Yeah, everything is PLA. I think. Yeah.
Okay.
I don't have TPU.
I was going to suggest,
TPU.
I was going to suggest doing the outer wheels with TPU.
Yeah, I haven't bought TPUs yet. Yeah, but all the parts done here in the left side are with PLA.
All right. Any closing remarks? Right. If not, it's next week is you, Rhett, right?
That's right.
All right.